Hello there. In recent presentations, we have discussed z-tests and t-tests. Now, these tests are basically the same test. The only real difference is that the t-test is more robust at smaller n's than the z-test. And this is because, to reiterate, the critical values of t are based on the t distribution instead of the normal distribution that critical values of z are based on. And so when we run either a t-test or a z-test, what we're getting in the end is a point estimate. Now, a point estimate is useful. It tells us if we have achieved significance or not. However, sometimes it's nice to visualize our data to really see what's going on. And for that, we can use something called a confidence interval. With a confidence interval, often abbreviated CI, we get to see the range of values for that alpha level. And so what does this formula look like? Well, it begins here. It's equal to x bar plus or minus z critical times s of x, that substitute for the standard error of the mean. So this plus or minus here means that we really have two different formulas. We have an upper bound, u upper is equal to x bar plus z critical times s of x, and our lower bound which is equal to x bar minus z critical times s of x. So let's run through this. When I'll separate these out. So let's say we're looking at number of pictures people take in a day. And so for calculating our upper is equal to, let's say, 13. X bar is 13 plus z critical. Well, because we have an upper and a lower bound, all confidence intervals are two-tailed. So that means that if we chose the 0.05 level, we would have to use 1.96 as our critical value of z. If we wanted to do 0.01, we could do that. And instead we'd use 2.57 as our critical value of z. However, we're just going to stick with 0.05 since that is the more common alpha level, the p-value level in psychology. And let's see. Then we need our estimate here. Let's say that standard deviation is 3 over square root of n, so let's say 25, which is going to give me 3 divided by 5, and I need a calculator. 0.6, okay. So times 0.6, and this is going to give me 13 plus 0.6 times 1.96, so 1.76. We could round that to 1.18 if we wanted. And so for our upper bound is equal to 14.176. Now we get to work on our lower bound. For our lower bound, we again have 13 because that's our x bar, that's our mean for this sample, minus, and we could go through and recalculate this again. However, the numbers are the same, so we're just going to bring them down. 1.176. So we have 13 minus 1.176 is equal to 11.824. And so there you have it. This is our 95% confidence interval, that alpha of 0.05 level, for this imaginary scenario where X bar of 13 pictures a day, standard deviation of 3, N of 25. And so that ranges from 14.167 to 11.824. Now, we're not going to go all the way into interpretation, but typically, when your confidence interval does not include 0, if you were to run a regular z-test, you would achieve significance, because 0, the sort of the null option of there is no difference, isn't one of the possible values. Now, there is one other trick we need to know. But before we get there, it's not typical to write this direction. It would typically be 11.824 to 14.176. I just happened to get it backwards from the way I chose to do this. But typically you'd see lower bound, upper bound. Just convention. All right, so now on to that tip. Since z and t-tests are basically the same, as we've already discussed, we can create a confidence interval for a t-critical instead of a z-critical. And this is because t is still more robust than z at low ends. And so if we have a low end like this one, N of 25, that's way low. It would have made more sense to calculate this as a critical value of t instead. And that would give us a more conservative estimate, which would mean a wider boundary. I will leave that for you to solve, however. And until next time, cheers.